We're going to begin this discussion on using the theorems and the postulate that we made our table with after making our geostrips and finding some properties about those parallelograms. So the first thing I want you to recognize is the symbol that's used for parallelogram, which is this little symbol here. Looks like a parallelogram. Whenever you see that and you see it in front of those 4 capital letters, you know that they're referring to a parallelogram, and so you can use the properties of parallelograms to solve problems and answer questions. The first question that they want us to find here is, what is the length of SV? Now remember that we learned that diagonals bisect each other in a parallelogram. We'll put some markings here on both of these. So if I wanted to know what was congruent to SV, we could say that VQ is the other half of the diagonal. So that's the segment that's going to be congruent to SV. So for a parallelogram, let's draw a little parallelogram symbol and an arrow. Diagonals bisect each other. So notice in the instructions it says to justify your answer. So that's what we're doing right now. We're justifying using the theorems that we developed the other day. This number 2 is asking us actually to find a triangle. It wants to know what's congruent to triangle VRS. So if we're talking about what's congruent to a triangle, you need to find another triangle. Well, remember, we just showed that these diagonals bisect each other. We also know from previous work that vertical angles are congruent. So here we can see that we have a side angle side triangle congruency. So we can name the triangles. If I named triangle VRS, we want to name the angles that are congruent. Now remember, alternate interior angles are congruent. So this angle SRV is the same measure as this angle VTQ. So that'll help us with our order. So triangle VRS is going to be congruent to triangle VTQ. The last question on this problem is naming which 2 angles are supplementary to angle TSR. So let's just look just at that angle. Let's get rid of all these markings. This is TSR. Now remember, opposite sides are parallel. So that means that consecutive angles are supplementary. And remember from our work in Chapter 3 that anytime you have parallel lines, that same side interior angles, if you looked at this as the transversal with these 2 parallel lines, that your same side interior angles are going to be supplementary. So we can say that we have this angle QTS is supplementary to angle TSR, and then also this angle right here, angle QRS, is also a same side interior angle up here. And we know that because in a parallelogram, I'm just going to put a parallelogram symbol and an arrow, consecutive angles are supplementary. You could also just use the theorem that we did back in from Chapter 3, that when lines are parallel, same side interior angles are congruent. Let's look at another example, and in all of these problems, we're going to actually look at measures of angles. So we're going to actually get their values, and then we'll look at a couple sides as well. So I'm going to start by looking at angle, looking at letter A, angle MJK, right here. And remember that we're dealing with a parallelogram, so let's just put in a parallelogram for all of these. I'm going to put a little colon here. We know that opposite angles are congruent. So here's the opposite angle to that, and if you look using your angle addition postulate, adding those 2 angles together, 30 and 70, you get 100, which means the angle opposite of it is also 100. So we can say that angle MJK equals 100 degrees. Looking at angle JML right here, that is a consecutive angle with the one that we just worked on, and also this 100 degrees angle here at MLK. So consecutive angles are supplementary, which means they need to add to 180, so that means this angle is going to be 80 degrees. So consecutive angles supplementary. Letter C, the measure of angle JKL is right here. Again, that's another opposite angle to a measure of angle JMK right here. We've got these two opposite angles, which means they're congruent. So since JML right there was 80 degrees, then we can also say JKL is 80 degrees. And our reasoning to justify that again is that opposite angles are congruent. And that's in a parallelogram. Since we're dealing with a parallelogram, we're just going to assume that that's what we mean for all of these. Now, KJL. That's not an angle of the parallelogram in itself. It's actually part of the angle. Let's take a look at that. We're looking at this angle right here, and you have these parallel lines, JK and ML, and you have this transversal JL. I always like to look for that Z when you're trying to identify alternate interior angles. Notice that you can see them here and here. So if this angle MLJ right here is 30, then we can say KJL is also 30 degrees, because from our previous work in chapter 3 again, if lines are parallel, so I'm going to put parallel lines. I'll do a little arrow there. We know that alternate interior angles are congruent. The last two examples we're going to deal with the sides. So if I looked and I wanted to figure out what A was, oops, notice that the opposite sides are congruent in a parallelogram. So I can make an equation that says 3A equals 21. And that is because opposite angles are congruent. And if I solved that by dividing by 3, we would get A equals 7. Looking at letter F, trying to find B. We're going to clear this so I can extend the page. We actually want to find what B is, and if we look back down at that, we can see these opposite sides right here. JK and ML, and that those are congruent. So we can write an equation that says 2B plus 3 equals 45. So that's what we're going to do right now. So 2B plus 3 equals 45. And then we can just solve that algebraic equation. So I'll subtract 3. That gives me 42. And of course, when you divide 42 by 2, you get B equals 21. So we use the idea again that opposite sides are congruent on both of these if I were going to justify my work. So it was on that one, and it was on letter F. This one I just want to point out a proof for you. We're given that parallelogram XYRZ, and that WZ right here is congruent to WS. So that would be these two sides right here. Well, if we looked at that triangle, that means we have an isosceles triangle that makes these two angles congruent right here, angle Z and angle S. So when I looked at my steps of my proof, I put down my given, and then you notice that in my next statement I said, I have an isosceles triangle by definition of isosceles triangle. Since I have an isosceles triangle, I can go ahead and use the fact that the base angles are congruent. So that's why I put angle Z is congruent to angle S by the isosceles triangle theorem as my third step. Now I want you to notice that since we have a parallelogram, that opposite angles are congruent. So we can also say that angle Z is congruent to angle XYR, because opposite angles in a parallelogram are congruent. That leads us to our last step, where we can just use a substitution or a transitive property to say our final step in our proof, that angle S is congruent to angle XYR. and it's just a substitution. And if you notice that you have z in both of these, so s and x, y, r are both congruent to z, so they've got to be congruent to each other. So that's a look at one of the proofs in your homework, and we'll start in class with a warm-up with another one. That's all we're going to talk about today. You can look at 8.2b for your second lesson. You can consider this to be 8.2a, and the next video that you'll watch will be using some coordinate geometry to do some proofs.